Hello, everybody. We're going to be doing a few examples for graphing rational functions. We're going to try to make sure we understand the characteristics, such as the intercepts, the asymptotes, and that will help us determine the shape of this general curve. We've already discussed the branches that form the two curves on our rational function, but we're just going to get into more detail with each of the characteristics. I'm going to start with one like this. I'm going to follow with one similar to it, but a little different numerator. Please know the differences between the two of those is what happens to our horizontal asymptote. So that's a discussion piece you're really going to want to listen to. That seems to be, that horizontal asymptote, that HASI, seems to be the one that causes some issues. So when we get there, please listen. All right, so let's get started here. I don't have a graph like I do the second one, so let me quickly draw a grid. Now there's a time and a place, obviously, for some digital Desmos and graphing calculators that are really useful. But what we're really working on in this lesson is the number sense of a rational. Do you understand what happens to a fraction and how it compares a numerator's work with a denominator's work, and how we can peel back all these layers like an onion? And that'll really tell us everything we need for the graphing and the curves. So we are talking number sense here, and once you work on stretching your number sense, you're only going to become a better mathematician. So domain, that means what x values work and what don't. You know it's a fraction, so you know that you have to be careful in the denominator, and you know that this is an issue here. You don't want the denominator to be 0, so you know you can really never work with -3. That not only tells us in interval notation what our domain is going to be, meaning jump over that -3, we don't really want it, keep going to the left and right. That's just the domain. It's just a fancy way in interval notation to write what's allowed. In doing that same discussion, you just got done telling me where your vertical asymptote is. Your vertical asymptote is at -3. You're telling people visually now, not just algebraically, but you're also telling them visually, hey, stay away from -3. Your curve will not go there. It's going to gravitate towards it, but it won't go there. So I'm just going to remind myself that at -3, we just have to be careful. The horizontal asymptote is another guidance line. So these are guiding lines that dictate where the curve goes. The horizontal asymptote, though, is you understanding how the numbers work in the numerator compared to how the numbers work in the denominator. And when you compare how they grow, what actually the whole fraction turns into. So there's two ways to do this. Plugging in a large number of 0. So you could say, I'm comparing -3 to, like, I'm going to plug in 100, like to 103. Like putting in a really large number far off to the right and asking yourself, where does this curve go? Well, that's really a tiny, tiny fraction. That's getting really close to 0. So that's one way to say what your horizontal asymptote is. But the other way is to look at the powers in the numerator and compare them to the powers in the denominator. We call those degrees. So in this case, the degree of the numerator is a 0 because there is no x value there at all. So it must be gone, and so that degree is 0. Your degree for this power is 1 because there's 1x there. And when you look at that, you're saying the degrees of the numerator are always smaller than the degrees of the denominator. Oops, I'm sorry, denominator degrees. In other words, what's happening is that bottom's getting super fast every time you go to the right. And when it gets that fast compared to the numerator, it always turns to 0. So in this rule situation, your horizontal asymptote in every case will always be y equals 0, which in essence is the x-axis. So I'm going to make this red just so you can see it. And then just so you understand guiding lines and how they act, I'm going to make the other one red as well. So these are going to guide our curves, but we don't know where to start the curve because we don't have points. So that's where you go to the intercepts. They are your opportunity to get your points and sweep the curve. Well, we have an issue because x-intercepts normally tell us to go set 0 equal to y and substitute that in, work out your equation, get the denominator out by multiplying both sides, and try to solve for x. Well, the minute you multiply both sides by the LCD, you're going to get 0 equals -3, and that's a false statement. We knew that we had an issue. There are no letters in the numerator, so there's no x-intercept. So since this is false, Since there's no x in the numerator, this is why we know that there are no x-intercepts in this specific problem, which made sense because that's why we dotted it out. So we need to find a point somewhere else. Let's find it on the y. That means literally 0, comma what is going to turn into that point. So we're going to substitute into the original problem that 0 to hopefully find, like making a table kind of, where that's going to be. That's looking really nice. So we're going to get -1, so 0, comma -1. That is beautiful. I now can see how my curve is hugging. It's going to hug this asymptote, sweep through there, hug this guy, and forever go close to 0. We understand that the other one, because we understand parent graphs, remember the parent graph of a 1 over x parent usually looks like this. So we understand that curves, branches are usually opposite of each other, typically in that situation. So we probably get that it's over here. We don't know where it is, so let's make a table of accuracy here, and just so we can get a little bit more accurate. I think, let's see, let's just go to the left of -3 a little bit, -4, and let's see what happens when we substitute that in. That's going to look really nice there. That's -3 over -1. So back 4, 1, 2, 3, 4, up 3, 1, 2, 3. There's your dot. Hug, 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 sweep, hug, hug, hug. Now I want to have one more discussion with you, because there's your graph. There it is, your 2 branches. It looks very similar to the parent. It's a little bit stretched. We knew that was probably going to happen because of that -3 out there. That's kind of like a growth factor. So the deal is, there's something that you can also look at near your VASI. Let me have you look at the denominator. That will help you with deciding where this curve goes compared to this curve. Especially will confirm your table. So look at the VASI factor and look at its power. If the VASI factor has an odd power, then as your growth or your curve approaches the VASI, as it approaches 3 here, it'll have opposite behavior. In other words, it's going to go up on that side of the VASI, but it's going to go down on that side. Opposite behavior, all because of an odd power. That's another way to check if you've got your curves in the right spot. Let's try another example. So now we've got a little bit of a difference here because we have that 4. So let's figure out our exclusion and then see how that 4 works. Exclusion can't be -2, so that means I'm going to jump over it, not use it, go to the right and left. There we go, that's my VASI at -2. So let's get that in there. PASI, let's look at the powers. The numerator power, if you look at its degree, is equal to 4. Or no, I'm sorry, I apologize, 1. Silly me. There's the 1 there. The denominator's power, or degree, is also 1. There it is. So this rule means we need to take the coefficient 4 with the coefficient 1 and divide those out, and that's going to be 4. So we're all the way up here. Now what that's really saying is, if essentially you put 100 in here, you get about 400 over about 100 as you got large to the right. That's another way of describing why you get 4. The rules here is very specific and algebraic. X-intercepts. Let's take that 4x minus 8 equals 0. Move the 8 over. Okay, that's going to be moving the 4 over. We're going to get 2. So let's put that 2 there. Now I can almost see the curve coming out, but I need more. So let's do the y-intercept. Substitute 0 in for the x's so that you can get this 0, comma y business. Work that out. You got -4 in the numerator. You got +2 here. You're going to get -2. So at -2 there, look at that. That's getting a little bit better to see how you, from down here, you hug, and then you scooch off to the right so that you never ever cross that 4 there. We now need to figure out what's going on at the top. So I see this 4 out here. If I would have factored my fraction, which is always good to do, I see that there's a growth of 4 So I know I'm probably going to go 1 over and 4 up. I know I'm going to probably be high up here. If I don't trust myself on that discussion point, I can always plug a number in and try that closely. If I do that, let's see, let's go to the left just to -3, and let's put 3 in. I'm going to put 3 over here because it's going to be quicker. 4 times 3 minus 2 is 1. 3 plus 2 is 5. I've got -3. Oh, merciful heavens, Mrs. Brigham did her math wrong. Backwards, people. Sorry. If I put -3 in here, it's not what I got earlier. So let's see. We've got -3 also at the bottom. There we go. We've got 4 times -5 all over -1. That's -20 by -1. That's +20. Merciful heavens. Yeah. So that does look like we go all the way up here, really high. So there you go. There are your two curves. That makes a lot of sense because look at that factor being odd. So if this heads up, then opposite behavior heads down. That kind of gist is what we're doing for rationals. Obviously a lot of detail. Practice makes perfect here in understanding it. And always when you're done, if you want to check a graphical tool, that's fine, but that should not be your first case. So watch this over and over again. Reach out if you've got questions.